Hey, Block 8, I figured it would be nice to end the week with a little lesson, personal message from me, and quickest way, easiest way for me to know that you got the message about special right triangles in lesson 9-2. This is the second lesson of this chapter. The first one was on Pythagorean theorem, and not only Pythagorean theorem for right triangles, but also those inequalities that you could tell if you plug numbers in from a triangle and they don't fit the Pythagorean theorem, then you can tell whether it's acute or obtuse based on how the c squared part comes out compared to the rest. C squared greater than a squared and b squared, then you have an obtuse triangle. C squared less than a squared plus b squared, you have an acute triangle. All right, so moving on to this section, we are going to talk about two special types of right triangles. The first one is a 45-45-90 triangle. These are very common because there's symmetry to them. The two legs are equal. There's a right angle. This could be thought of as half of a square. And they're so common that rather than always plugging in values to the Pythagorean theorem to solve the triangle, it would be good to know that there are some special relationships among the sides of this kind of triangle. Specifically, theorem 9-4, or whatever number it might be in our textbook now, says the hypotenuse will always be radical 2 times as long as each leg. And each leg is going to be equal in a 45-45-90 triangle. Think of it as half of a square. All the sides here would be equal. Cut it in half, you get each of these 95 and each of those equal. All right. Now, why is n times radical 2 always going to be the value of the hypotenuse? Well, it just comes from plugging into the Pythagorean theorem. If you call this A and you call this B, because those are the legs, and this is the hypotenuse, you know, very important to be able to pick out the hypotenuse in a right triangle. It's always across from the right angle. Anyway, we call that C. So if we put into the formula a squared plus, this is going to be a little slow with the mouse, b squared equals c squared. I'm going to try now switching to a different way of writing on the screen. Anyway, plugging in 2a squared plus b squared equals c squared. If I put an n for a and I put an n for b, the next step to solve this to figure out the hypotenuse would be add together n squared plus n squared. Now, little algebra review here. This is like one n squared, and that's like another n squared. So to add two terms together that have the same variable part, we keep the variable part n squared, and we add the coefficients. 1 plus 1 is 2. So 2n squared is the same as c squared. Now, in order to solve this, we have to take the square root of both sides to get rid of the c squared. So what that does, pretty much the squaring and the square rooting cancel each other out, leaving c by itself. But over on the right-hand side, the left-hand side of this equation, we could split up, if you remember your algebra radical rules, you can split that into two separate radicals, square root of 2 times n squared. And then you can simplify the square root of n squared because, once again, square root and squaring cancel each other out. They are inverse operations. So that leaves us with just n times radical 2. And that's where this comes from. N times radical 2. Comes from the Pythagorean theorem, but we're going to memorize it and just use it when it becomes convenient. So we can take it as a shortcut to not have to go through the Pythagorean theorem every time. Okay? Let's look at the second kind of right triangle. Now this one also is pretty common that you'll have a right triangle with a 30-degree angle and a 60-degree angle. And there are special relationships amongst the sides in a 30, 60, 90 triangle. And they are worth getting to know and recognize. Here's the deal. We're going to say that there are 3 different sides to this triangle. There is the hypotenuse, as usual. because it's a right triangle, and that would be the longest side, and it would be across from the 90-degree angle. Be able to pick out the hypotenuse in a right triangle. Very important skill to start with. Then there's always going to be a shorter leg, and in this case, we have it labeled N. Now, how do I know it's the shorter leg? Well, it looks like it in this diagram, and if a 30, 60, 90 triangle is drawn to scale, it will always look like the shorter leg is across from the 30-degree angle. That's just a general inequality within triangles we talked about before, that the shorter side will be across from the smaller angle, and the longer side will be across from the larger angle. So this is the longer side here. Okay, the relationship between them is that the hypotenuse is always 2 times as long as the shorter leg, and the longer leg is just the shorter leg times radical 3. That's the relationship. Now, where does that come from? Once again, it comes from plugging things into the Pythagorean theorem. You can see if you look up these notes on the Google Classroom, I made a little diagram that shows, I'll just kind of sketch it out here, how a 30, 60, 90 triangle can be the result of cutting an equilateral triangle in half, like so. If this is 60, 60, 60, well, if you cut it in half like that, you end up with the top half looking just like this. So if we know that this side is, let's say, if this little piece is n, well, this whole side would be 2n. And so would this whole side be 2n. Okay, so there's why the short leg compared to the long leg, the short leg is half of the hypotenuse, and the hypotenuse is twice as long as the short leg. And then why is this side going to be n times radical 3? It's just because if you put n and 2n into the Pythagorean theorem, like so, n squared plus b squared equals 2n squared, and then you solve that, you will get n radical 3 for b. Okay, you can see that all on the notes on the Google Classroom. You don't necessarily have to write that down right here. But if you're curious, why is it like this, you can go ahead and look that up. All right, so let's move on to the examples of how we would use this. Example 1 shows a baseball field where at each plate there are 90-degree angles, and this imaginary line from home plate to second base could split it up into two 45, 45, 90 triangles. So if we are to calculate how far it is from home plate to second base, if the distance from home to first base and third and everything in between is 90 feet, then we're going to apply the 45, 45, 90 triangle concept, that the hypotenuse is just the leg times radical 2. So the distance, I'll just call it D. No, let me go back. It would make more sense to call it C, since that is the hypotenuse of the triangle. C equals radical 2 times 90. Now, 90 radical 2 is probably how we would write that more likely as a simplified math expression. 90 radical 2 would be more commonly how it would be seen, just commute those two terms there. But if you're talking about a baseball field, most people don't want to talk in terms of radicals, so we would probably plug this into a calculator to get the approximate value. And I'm going to use one of these calculators from school. I am going to, I don't know if you guys can see this on the screen. I will try to hold it so that you can. Going to plug in 90 times second square root of 2. I'm going to press enter. Okay, notice that when I press enter, my calculator just says 90 square root of 2. And you might be saying, well, how do I get the decimal version? Guess what? There is a little toggle button on this calculator that's right above enter. It's this little double arrow. If I press that, it turns it to the other version, which is the decimal, 127.3. Okay, so that's my answer, 127.3. And that would be in the same units as the side. That would be in feet. So it's approximately 127 feet. Okay, next example. If two equilateral triangles which measure 4 inches on a side are put together to form a rhombus, what would be the measure of each diagonal of the rhombus? Well, I think if these are equilateral triangles, it's pretty obvious to say this diagonal that goes from corner to corner of the whole rhombus, that would be the same as the other sides, 4. And the other diagonal would go from this corner to that corner. These would, as all rhombuses have diagonals perpendicular, they form a 90-degree angle. So within these small triangles here, we have got a right angle. Okay. And since these two sides are equal and this side is equal, this is going to be a 60, 60. Each of these is 30. This is definitely 30, 60, 90 triangle in here. The smaller angle is this one. This would be 30. And it's across from the smaller side. This would be 60. Okay. So if we just focus, I'm going to change colors here. If we just focus on one of these little right triangles, we've got the hypotenuse is 4. The relationship between the hypotenuse and the short leg is that the short leg is half of the hypotenuse. That would be 2. Well, that makes sense because this whole diagonal was 4. So that equaling 2 makes sense. And I'm making a big mess. I'm going to erase some of that right now. But anyway, if that's 2, the long leg is going to be radical 3 times the short leg. So this part down here is just going to be 2 times radical 3. And therefore, the measure of the entire diagonal from this corner to that corner is just going to be twice that amount. So the one diagonal is going to be 4, and the other one is going to be, this one is going to be 4 radical 3. That's the exact value. Okay. So we've done an example with 45, 45, 90 triangle here, and we've done one with 30, 60, 90 triangle there. Now let's just practice a little more. In this 30, 60, 90 triangle, the right angle is A and BC is not the longer leg the way that it's labeled here. It says, this should really say AC is the longer leg. Fix that on your notes. That should say AC. As we can see in the diagram, BC is the hypotenuse. So, typo, sorry about that. But anyway, find the length of AB. Well, AB is the short leg. So if we take the hypotenuse and just divide by 2, we get the short leg. See, I barely even had to write anything down because these relationships are pretty simple. If I memorize them, I can take these shortcuts. Okay. Then find the length of AC. That's the longer leg. It's always easiest to start with the short leg to get to the long leg. Just start with the short leg and multiply by radical 3. So the answer here is 7 radical 3. That's it. Okay. Moving on to example 4. Triangle ABC is a 30, 60, 90 triangle with right angle A. And once again, BC is not the longer leg. AC is the longer leg. This time, AC is labeled as 14, and it is the longer leg. If we want to find the length of AB, going from the longer leg back to the shorter leg is actually the most complicated thing in one of these problems. Because if this is N, This is n radical 3. That's what the notes say. That's what the theorem says. So if n radical 3 is 14, n radical 3 equals 14. I'm going to start writing on this paper. Then how do we find n? Wow, that came out terrible. It's a learning process, getting used to how to do this on an electronic copy. Okay, so if n radical 3 is equal to 14, how do we find n? We have to divide, and I like to do this in a separate color, divide both sides by radical 3. So we end up with canceling out. Well, that equals 1. N equals 14 over radical 3. Now that, if you remember from algebra, is not an acceptable way to give a radical answer. We never give the radical on the bottom. So if we were going to give this in simplified radical form, or acceptable to mathematicians radical form, we would rationalize the denominator by multiplying both the top and bottom by radical 3. Remember this from Algebra 1 last year? We're not going to forget our Algebra 1. We're going to just assume you know how to do this. What this does is we end up with 14 radical 3 on the top, and on the bottom, square root of 3 times square root of 3 is square root of 9, or just 3. So now the top has the radical in it, not the bottom, and that is more acceptable format for radicals. 14 radical 3 over 3 is the exact answer for AB. Okay, that's it. You can circle that. Hopefully you wrote neater with your pen on the paper. But anyway, once we know that, this is 14 radical 3 over 3. To find the hypotenuse, we're just going to double that. So BC would be 14 radical 3 over 3 times 2, which is the same thing as 28 radical 3 over 3. If I just multiply the top, if I just multiply this fraction by 2 times 2 over 1, it's just going to multiply the 14 times 2, that's 28. 28 radical 3 over 3. And that's the answer for BC. All right. The next example shows a ramp that is used to unload trucks. Truck drives onto the ramp. The ramp lifts up at a certain angle to tip the contents to pile out of the truck or fall out of the truck. How high is the end of an 80-foot ramp when the tipping angle is 30 degrees? Now keep in mind, here's the ramp 80 feet. Once it is tipped up, the bottom is not 80 feet. The ramp is 80 feet. So 80 is our hypotenuse. Okay. And this is the 30-degree angle. So assuming that this is a right angle because of just dropping straight down perpendicular to the ground, we have a 30, 60, 90 triangle. So for this first question, how high, we're basically trying to figure out this. How high is that? It's just the short leg of a 30, 60, 90 triangle when we know the hypotenuse. If you flip back to the very first slide again, oh, sorry, second slide. Remember, hypotenuse is twice as big as the shorter leg. So hypotenuse is 80, that is twice the length of the shorter leg. So the height of the ramp will be 40. That's the answer. I know this does not look pretty, my writing in electronic form, but we're getting our answers and we're just going to make the best of it. So this is a separate question. What if the ramp was raised at a 60-degree angle? Then what we would be looking at is, and I'm just going to redraw it really quickly over here. If the 60-degree angle was there, and that's still a right angle, and that's 30, and this is 80, now what we're trying to find is the longer leg But in order to find the longer leg, you got to go around and find the shorter leg first. So from 80, you have to divide by 2 to get the shorter leg is 40. Then what's the relationship between short leg and long leg? It's times radical 3. So the answer would be 40 times radical 3. And that is the simplified answer, 40 radical 3. Again, you can see these answers on the Google Classroom calendar. There's a link to a nicer written copy of this, but I'm trying to use this to explain everything as I would in class. All right. If it were 45-degree angle that it was lifted the ramp off the ground. So these are each 45, and that's your 90. If your ramp was still 80 feet long, how high would it be? Well, this is one we have not done before. You have to know that the relationship between in a 45, 45, 90, the hypotenuse is radical 2 times the leg. But this is kind of backwards. We know the hypotenuse, and we want to get back to the leg. So 80 is radical 2 times the leg, which we don't know, so I'm calling it x. So what do we have to do to find x? We have to divide both sides by radical 2. And therefore, x is equal to 80 divided by radical 2, which we should simplify by rationalizing the denominator. And when you do that, your final simplified radical will be, I'm just going to 40 radical 2, okay? Because you would multiply top and bottom by radical 2. You'd have 80 radical 2 over radical 4. Radical 4 on the bottom would be just equal to 2. The 80 divides by 2, and you get 40 radical 2. But that's your final answer. If you want to give it as a decimal, plug it into the calculator and turn it to a decimal using that little special key that flips between radical and decimal. That is the bulk of our lesson today. There's one more challenge question here, which I did put the solution on the Google Classroom calendar notes, but I'm just going to point out and not go through this whole thing because I'm getting frustrated with this writing situation. But in order to solve this, given this figure and knowing that only these two are parallel, it's not a parallelogram. If you want to find the perimeter, you got to break down into parts. And there's a 45, 45, 90 triangle here. There's a 30, 60, 90 triangle there. You've got hypotenuse. You've got, once you figure out this height, this is the same height. So then you can use that to find this hypotenuse. And don't assume that this is equal to 24. It's all the way across, it's 24. So once you figure out this amount, you can subtract that off and know that this is 24 and then this is a different amount. Anyway, I'm going to leave this as a challenge extra credit question. If you do this problem, actually it's already done in the notes. If you want to do it, get it from the classroom notes. And that's your lesson for today. Next time, you'll be practicing some of this on the practice worksheet. But for today, this lesson and 30 minutes of Alex is all that you're responsible for. Okay. Hope you're doing well and you have a nice weekend. Bye.